Okay, so this is December 12th, 2011. This were number 3 and 4 were the homework for tonight. So these are the solutions worked out. We have a classic related rates problem here. This is from the 2008 AP exam, I believe. And so it says oil is leaking from a pipeline on the surface of a lake and forms an oil slick whose volume increases at a constant rate of 2,000 cubic centimeters per minute. That's important. And it's a rate. The oil slick takes the form of a right circular cylinder, with both its radius and height changing with time. Alright, so that's important too. They tell us what shape it's taking. Alright, so part A, we want to know at the instant when the radius of the oil slick is 100 centimeters and the height is 0.5 centimeters, the radius is increasing at a rate of 2.5 centimeters per minute. At this instant, what is the rate of change of the height of the oil slick with respect to time in centimeters per minute? Well, this is nice. It's pretty straightforward, and we know all but one of our variables. So we just need to kind of sort things out real quick, and then we'll go ahead and take the derivative of our formula and then solve. So we know the first thing they told us was the rate of the volume increases. All right, so we know that that's going to be represented by dv dt, the derivative of the volume with respect to time, or the rate of the volume. So that's 2,000 cubic centimeters per minute. Okay, and we know that R is 100, H is 0.5, and it was dr dt, the rate of the radius with respect to time, is 2.5 centimeters per minute. So we don't know this one. And we will go ahead and find that. So we'll take the derivative. We have our formula. We're going to have to use the product rule. So I'm going to kind of look at it like this: pi r squared times h. All right. So the product rule. We're going to take the derivative. We're going to first differentiate the volume with respect to time. Okay, so here we go with the product rule. Take the derivative here first. And don't forget that with respect to time. And h stays the same. While we add the first part times the derivative of h. Okay, so let's finish this up. We've taken the derivative of the volume of a right circular cylinder. We use the product rule, and we've also identified the things that we know. So we know R, H, dr dt, and dv dt. So all we need to do is be able to find out what is dh dt. We took the product rule, and we're ready to plug in to our derivative and find out what h is. So I'm going to use another screen here. So we have dv dt, we know is 2,000, and we have 2 pi r. R was 100, and we have times dr dt, which is 2.5, times h, which is 0.5, plus pi r squared, so pi times 100 squared, times dh dt. So I think I've got all the substitutions correct, and this is a calculator allowed question, so we would multiply here, here, subtract this from 2,000, and divide by our coefficient in front of dh dt. So we do that, and we find out that dh dt equals 0.038 or 0.039 centimeters per minute. So we're finding that the height is increasing by 38 1,000ths or 39 1,000 centimeters per minute. All right, part B. Part B says a recovery device arrives. That's great. The rate at which the oil is removed is R of T equals 400 times the square root of T, cubic centimeters per minute, where T is the time in minutes since the device began working. Okay, so now we have a situation where we know that the volume of the oil slick is increasing, but we also know there's a device that's taking some of it away. So oil continues to leak at a rate of 2,000 cubic centimeters per minute. We're going to find the time T when the oil slick reaches its maximum volume. All right, so the first thing we need to know, or we need to represent, is that we're told that oil continues to leak. It's being removed at this rate, and this is a rate. We don't need to take the derivative of this. All right, so we can take that at face value. So we can represent that as dV dt now, the total volume of the slick. We know that it's increasing at 2,000, but it's being removed at this rate. And we haven't got into that much for this class yet, but we do know that when the derivative is 0, that indicates that there's a maximum or a minimum, because the slope of the tangent line is horizontal there, and that will be, again, a maximum or a minimum. So we want to find out when dV dt is 0. Well, we know that 2,000 minus itself would give us 0. So dV dt is going to be 0 when our function r of t, the rate of removal, is also equal to 2,000. So we can simply substitute 2,000 as r of t and solve for t to find out that time. And we just need to go ahead and check and verify that it is a maximum. So we'll do that. So we have 2,000 equals 400 square root of t. Divide both sides by 400. We find out that 5 is the square root of t. And the only thing that that can be is 25. So we find that T is 25. Well, we know that when the oil started leaking, it kept getting bigger. So we know that the volume is greater than 0 between when it started and up until we found this maximum at 25 minutes. We also know that if t is 26 minutes, we're going to find that this number here, if we plug in 26, that's going to put us bigger than 2,000. So that means 2,000 minus something bigger than 2,000 is going to be negative. And we can never predict when the announcements will come on. So anyways, where we was, we're saying that we know that the oil slick is increasing from the time it started until we found this maximum or minimum at 25 minutes. So if we put in 26 minutes for t, we're going to get a number that's bigger than 2,000. All right, sorry, wrong sign. We're going to get a number that's bigger than 2,000. So 2,000 minus something that's bigger than 2,000 is going to be a negative number. So that means dV dt, the rate, is going to be decreasing. So that means that if the rate was increasing, you think about a rate as the slope of a tangent line, it's increasing, and then all of a sudden at 25, after 25, it's decreasing. That indicates that there's a maximum there. All right, for the minimum, it would be the exact opposite. We would have a negative slope of a tangent line, and then at a minimum, as soon as we're past the minimum, we'd have a positive slope of a tangent line. So that we know for a fact that 25 is the maximum, and that's where the oil slick reaches its maximum volume at 25 minutes. So the justification was necessary. All right, before the screencast gets a little too long, I'm going to try to find number 4. So we're going to take the derivative and show that dy dx is negative the quantity x plus 1 divided by the quantity 2 times y cubed plus 1. So derivative 2x plus 2 plus 4y d cubed, dy dx plus 4 dy dx equals 0. So we've got 4y cubed dy dx plus 4 dy dx equals negative 2x minus 2. We're going to factor out a dy dx. These are in common here. So I'm just going to leave that here and then take this and divide it. So I've got dy dx, and we would want to show those steps in between to get the full points for this, but I'm just going to abbreviate. So we've got negative 2x minus 2 all over 4y cubed plus 4. We can reduce each by 2, so that's where we get negative x minus 1 all over 2y cubed plus 2. Factor a negative out of our numerator, x plus 1. Factor a 2 out of our denominator, y cubed plus 1. So there we go. That is our derivative. Write an equation for the tangent line. Well, this is great because it gives us x and y. We know the derivative. We just plug in negative 2 for x, 1 for y, find out a slope of our tangent line, and then put it in point-slope form. So I'll just show the substitution really quick. dy dx equals negative 2 plus 1 divided by 2, 1 cubed plus 1. So we've got negative 2 plus 1 is negative 1. So negative 1 is a positive 1. 1 cubed is 1, plus 1 is 2. 2 times 2 is 4. So the slope of our tangent line is 1/4. We know that our x value is negative 2. Our y value is 1. In point-slope form, that is going to be y minus 1 equals 1/4. X plus 2. Plus because x minus x0, so minus a negative number, we have x plus 2. So that should be the equation of our tangent line to the curve. Okay.